In this video, we're going to introduce the idea of a double integral and give sort of a formal definition. But before we get to the matter of hand, let's take a step back and kind of remind ourselves of where the concept of a definite integral came from. And in fact, we have the classic problem. And let's just assume that we have a function. Let's say that function is always positive, so its graph is always above the horizontal. And then we define a region that has these four boundaries. So the x-axis from, let's say, x equals a to x equals b. Then we have these vertical line segments, and then we have the curve that bounds the region above. And then the question is, what is its area? So if we want to find the area here, well, what do? Well, we start with an approximation, right? And this approach is due to Riemann. You make your partition of the interval a to b with a predetermined number of finite subintervals. And let me just go ahead and label the x values. Let's say that's x0, we have x1, we have x2, ... and then all the way up, and I'll call b x sub n. Right, so we're using n subintervals here. And then what do? For each of the subintervals, we pick a special value of x. And it could be anywhere, really, but, typically we either use the left, the right, or the midpoint. So I'll just go for the midpoint just to illustrate this. So let's say we pick that x value, and we use the notation like x star sub k, something like that. And then based on this x, we can find the height of a certain rectangle, and that rectangle goes up, right? And essentially its height is the y value that corresponds to this x value. And then what do? Well, we create a rectangle with that height over that specific subinterval, and then we can compute its area, repeat that process for each of the subintervals, take the summation, and the sum of all the red regions, the area of all these triangles that I have, rectangles, that I have here in red, that gives us an approximation of the area under the curve. So let's write down, so we again remember what the notation looks like. So if we use the delta x to represent the width, right? So I'll say delta xk. If that represents the width of each of these subintervals, then the area of one rectangle is given by this. It's the height, which is this fk star, and then times the width, which I just denoted as delta xk, and then we sum all of these up. That's our approximation. But we don't want an approximation. What we want is the exact area. So the theory is we can make the approximation better by refining our partition. That means making our subintervals smaller and smaller, right? And there are different ways you could say it. So assuming we use uniform subintervals, we could say let n go to infinity, right? And provided that limit converges, or that this limit exists, so the limit as n goes to infinity of this expression, this is what we define as our area, or more generally, net area. That's for when functions change from positive to negative, or vice versa on this interval. So this is by definition, and the notation that we use is this, the familiar definite integral. Now, from this point, we develop other techniques. In fact, that's where the fundamental theorem comes in, and that tells us how to actually evaluate it. But this is the formal definition of our definite integral of a single variable, right? So what we would like to be able to do is to replicate this process, right, for surfaces, right? So let's see what we can come up with. So I'm going to draw my XYZ space, 3 space. And I'm going to make the surface relatively simple. I'm going to try to give the sense that it is curved. So let's say here's my surface, right? And so let's actually let me just go ahead and do this. So this is our surface now, and at least a portion of it. And let's say we have the explicit equation that defines the surface, and that equation is of the form z equals f of x, y, right? Now, what we're going to do is I'm going to sketch kind of a general region in the xy plane. So in the xy plane, I'm going to sketch a region, something that looks like this. And then what I'm going to do, so assuming that this region is in the domain of this surface, for every ordered pair in this region, not just on the boundary, but everything inside as well, right? What I can do is I can find the corresponding z value. And so again, I'll just indicate a few of them, but let's say this ordered pair corresponds to that z. Say this ordered pair corresponds to that z. Let's say this one corresponds to that z. Let's say one over here corresponds to that z. And then, so essentially I would get kind of it doesn't have to look the same as this, but what I end up getting is this region where the base is this region in the xy plane, and then the top of the region is the surface, right? So the space in between is some three-dimensional space. And we can actually think of it as let's say a space that can be filled with a certain amount of volume, whether it's a liquid, whether it's a gas, something like that. But we would like to be able to find this volume, right? So here is its base, and the top is defined by this curved surface, right? Or surface in general. It doesn't have to be curved. It could be a plane. But what we're about to do is to describe something that works for very nice surfaces, whether they're flat or curved. And in order to define something similar to what we did earlier with a single function, let's do this. So what I'm going to do on this side is sketch just the XY plane and sketch this region and kind of, indicate how things will work. So here's our XY plane. And here is our region. So now we're looking down from above on this region. And we're gonna try to as closely as possible mimic what Riemann did for a function of one variable. So instead of only breaking up the x, we're going to break up the x and the y interval as well. So for instance, I'm going to slice it vertically like this, and then I'm going to slice it horizontally like this, right? And what that does is, for the majority of the region, now it looks like I've broken up the region into these little rectangles, right? So let's again get some notation going. So on the x-axis, I'm going to use the same kind of labeling. And what I'm going to do is, this is going to be our x0, and then there's going to be an x1 and ... up to xn, right? And then do something similar on the y-axis. Now, I don't have to have the same number of, let's say, vertical lines as I have horizontal lines. So I don't have to use m here. In fact, I need to allow for a different number along the y-axis. So this will be, let's say, my y0, ... and I'm going to call this one y sub m, right? So essentially, I've broken up this region horizontally into n intervals, and then vertically m intervals. So basically, I have an n by m grid, right? Then, so what do? Well, in each of these little rectangles, we're going to pick a special ordered pair, right? So just like how before we picked a special x, now we're going to pick a special ordered pair. So let's say I just go for that one, and then I'm going to indicate what it is. So it's an ordered pair, so it has to has an x and a y value, and I'm going to call it x star I comma y star I, right? So this is basically from the ith little rectangle there, we pick one ordered pair. Now what are we going to do with this ordered pair? And let's say the ordered pair is right here. What I'm going to do is to find the corresponding z value for that ordered pair. So I'm going to indicate it right there. And then remember, that ordered pair came from this little rectangle. Let's draw this little rectangle now in the three-dimensional graph. And then that rectangle, again, it will define a rectangular solid where the top is, so let me draw another little rectangle here. And then let's connect this. So this vertex is going to connect to that one there. This one is going to connect to that one. The back one's going to be a little bit hard, but there we go. And then this other back one might be a little bit easier right there. And what we're going to do is find the volume of this rectangular box, right? Or you could actually call it a rectangular prism. And we repeat this process for each of these little rectangles here. So I'm going to pick a whole bunch of them, find a whole bunch of these, construct a whole bunch of these, find their volume, and add them all together. And that's going to give me an approximation of my green volume. So let's see if we can write down the expression for that. All right. So the general one, and I'll switch back colors here. So we have F, so I'm going to plug this ordered pair in to find that specific height. So it's going to be x star I comma y star I, okay? Now, so that just gives me the height. Well, in order to get a volume, I need to know the length and the width, or I need to use, I should say, the length and the width of my base. Well, I can look over here and see exactly what's going on, because as usual, I can call this distance here delta x, right? And what else can we do? Well, let's see, I can call this distance here delta y. So in fact, let's go ahead and, yeah, let me label this sub I and then sub I, right? So if I take the height of my rectangular solid and multiply by the length and the width of its base, so let's just do delta xi delta yi, that will give me the volume of one of these solids, right? But then in order to add them all up, I have to add them all up in the x direction and also in the y direction, because I have them going this way and this way. That means I have to do what's called a double summation. So it looks like this. And in the x direction, so basically this sigma sign will correspond with the x's. And again, in that case, I goes from 0 to n, right? Because we have n of them in that direction. Actually, let me write it this way. Yeah, I need to change. So I'm going to, yeah, because these are, let me do one thing here. This, I'm going to make this one J. Actually, no. Yeah, these J. Because the subscripts don't have to be the same. So J and J. So then I could say that I goes from uh, 0 to n. And then j for the y goes from 0 to m. And this will give me the approximation of my solid. But if I want it to be precise, what do? Well, again, I do what Riemann did. I would make my grid finer. I would do what's called a refined partition and simultaneously make my delta x and my delta y's get smaller and smaller. The way I can do that, again, if I'm using a uniform delta y and delta x, I would take a limit as both m and n goes to infinity. So I'm going to put one little limit sign here, and then I'm going to say n is going to go to infinity and m is going to go to infinity. And if this limit, this double limit, if you will, exists, this is what we define as the volume of the solid that is bounded above by this surface and this region, right? Let me add another piece of notation here. It's a lot of notation in this, right? So we have our R there for region. And but obviously writing this, right, just like how we don't use the limit of the Riemann sum to denote a single integral, we're not going to use this double limit of a double, I guess you could say, Riemann sum to represent a double integral. So what is our notation? What are we going to use? Well, this is the definition. So in when we had just one independent variable, we had one sigma sign and we had one integral sign. Now, since we have two sigmas, we're going to use two integral signs. And instead of integrating over an interval from a to b, we're essentially integrating over this entire region. So we put the r as kind of below the double integrals, saying that this is the double integral of, and here's my function, right? So we have the f of x comma y. So it's the double integral of this surface over this region. So what do we do with the delta x and the delta y? Well, this calculation here gives me the area of the really tiny rectangular base. So this is really an area, but it's a really, really small area. So we actually refer to this, so the notation that we use is we're going to use D and an uppercase A to say that this is the small area of the little rectangular base of our solid. So you can think of this as the area of the base times the height. That gives me the tiny volume, and then the double integral sums up all of those tiny volumes to give me a nice, precise, exact volume, right? And now, so the illustration that's drawn here, again, just like when we're developing the Riemann sum with one function, we drew the curve so that it was above the x-axis. Here we drew the surface that it's above the xy plane. But technically surfaces can be both above and below. So if the surface, in other words, if your z changes from positive to negative values over this region, what we would actually be computing is what we call the net volume. Because some of the function values would be positive, some of the function values would be negative, and when you add them all together, which is what your summation will do, you'll get a net value. So let me write out in words what this symbol represents. So this is the net volume. You could say solid or region. It's just a three-dimensional region, but I'll go ahead and say the net volume of the solid bounded by our surface z equals f of x comma y, and the region R in our xy plane. So, and the region R, I'll just say, in the xy plane. And again, this is all predicated on the assumption that this limit exists. And so this is the definition, or our definition, of a double integral, right? So in this video, I wanted to take the time to sort of develop this concept. And then in subsequent videos, we will take a look at like what these solids or regions might actually look like. And then the big thing is, how do we actually calculate this, right? And you'll see that it's actually not that difficult, which is nice, right? We are going to be able to utilize a lot of the concepts from our single definite integral, and now we're going to look at double definite integrals and so forth. All right, so if you want to see what that's like, hop on over to the next set of videos, and I'll see you then.